Hello everyone, today we're going to be working on problem 3, and this problem is saying that for the beam given below to derive the moment functions for regions A, B, and B, C, to use the position variables that are shown below with the origin starting at A, and to provide the function units and the valid limits of each position variable. So what we're going to be doing is, the first thing that I'm going to do is I'm gonna determine that concentrated force of this uniform loading that I have in the beam from the span AB. So to do that, I'm gonna call that concentrated force F1, and we know we could find that by multiplying 50 pound-feet by the span, which is 20 feet. Our feet would cancel out, giving us just that force. So we would have a force of 1,000 pounds. And since we know that this is a constant or a uniform loading, we do know that that will be found mid-span of that loading, which would be 10 feet starting from point A or 10 feet from point B. It doesn't really matter since it is 20 feet. So 1,000 pounds. From there, our next step would be finding the values of our reaction. So at point A, we have a pin support, so we would have two reactions, our vertical reaction and our horizontal reaction. And then at point B, we would just have one vertical reaction. So to solve for our reactions, I'm going to be taking the sum of the moments at point A to solve for my B sub y, since with doing that, my reactions at A will not be creating a moment. So counterclockwise positive, the sum of the moments about point A have to equal 0. My reactions at A will not be creating a moment. We have my 1,000-pound concentrated force acting downwards. We know that it's going to be creating a clockwise moment, meaning a negative moment, with a force of 1,000 pounds times 10 feet. From there, we have our reaction B sub y that I assume that will be going upwards. So it will be creating a counterclockwise moment, meaning a positive moment. We don't know the force, but we do know the distance of 20 feet. And then from there, we have this moment that is going clockwise, so a negative moment of 2,000 pound-feet. We know that all of this has to equal 0. So from here, we would just be simplifying. So 10,000 pound-feet plus 20 by minus 200 pound-feet has to equal 0. So we would solve simply for our reaction B sub y, and that would give us a value of 510 pounds. And since we got a positive number, that means that we assumed correctly the direction of our reaction. So we do know that our reaction is going to be going upwards. So 510 pounds. So now that we know that, I'm going to be taking the sum of the forces in the x direction to solve for our horizontal reaction. But as you guys could see, it is our only force in the x direction. So we do know that that one will simply just equal 0. But we still have to show the work. And then from there, I'm going to be taking the sum of the forces in the y direction to solve for my last vertical reaction. I assume that our a sub y will be going upwards, so that's positive. We have that concentrated force of the loading acting downwards, so that's negative. And then from there, we have our other reaction that we already solved for, acting upwards, so that's positive. We know that all of that has to equal 0, so we end up getting that our reaction has a value of 490 pounds. And since we got a positive number, we do know as well that we assumed correctly and that the reaction will be acting upwards. So now that we solved for all of our reactions, the next step would be now looking at each of the regions to solve for the moment and functions. So I'm going to simply move this on to the side. And I'm going to move this also to the side. So I'm going to start off with region AB. So this is going to be the work for region AB. So as you guys could see, our X1 is somewhere around here. There isn't a specific location. That's why it's given to us as a variable. So X1 is technically anywhere from here before that 20 feet. So we're going to draw a free body diagram of that. So we have our beam with this concentrated force. We have a pin support here with our reaction of 490 pounds acting upwards. We don't have to draw this one in because we know that one is equal to 0. We don't know what that concentrated force is going to equal to because we don't know how far this cut is, since we're just putting the span as x1. But what we do know is that this concentrated force is equal to the 50 pound-feet multiplied by x1. And we know that our cut is right here. So from here, we're simply just going to include our shear and moment based on sign convention. So we do know that our shear, since our cut is to the left, is going downwards. And then our moment will be going counterclockwise. So to solve for our shear moment, we would simply just be taking the sum of the moments about the cut and just take the sum of the forces in the y direction for our shear force. So upwards positive, the sum of the forces in the y direction have to equal 0. So from there, we would have our 490 acting upwards. That concentrated force we know is equal to 50 pound-feet multiplied by x1. And then we know our shear force is going downwards. We know that all of that has to equal 0. So if we were to solve for this, we know that our shear force equals 490 pounds minus 50 x1. So this is our function for our shear force. And we know that this is true. Meanwhile, let me move this a bit more to the side. We know that this is true. Meanwhile, our x1 is greater than or equal to 0 and less than or equal to 20 feet. So this is our function for our shear force. And this is our limits. So now for our moments, I'm going to be taking the sum of the moments about the cut. So counterclockwise positive, the sum of the moments about the cut have to equal 0. So we know our shear force will not be creating a moment. We do know that our 490 pound reaction will be creating a moment. It's going to be creating a clockwise moment. So that's a negative moment with a force of 490 pounds. We're going to multiply that by x1. From there, we have our concentrated force acting downwards. It's going to be creating a clockwise moment. So positive moment with a force of 50x1. And as for our location, We know that it is midspan of x1, so multiply that by x half of x1, so x1 over 2. And then from there, we have our moment. Sorry. Our moment that is going counterclockwise, so positive moment. And we know that all of that has to equal 0. So simplifying this a bit down, we would have negative 490 x1 plus 25 x1 squared plus m equals to 0. So we know that our moment is equal to positive 490 pounds times x1 minus 25 x1 squared. And we know that this is valid. Meanwhile, once again, our x1 is within the limits of 0 and 20 feet. So with that, we are done with region AB. So now our next step would be solving for region BC. So this would be if the cut is past that B point. So we have region BC. Now I know that in our picture that they're giving to us, it shows us that x2 will be from here to here, but doing it that way would be a bit complicated. It just takes a bit more work, but it is doable. So what I'm going to do instead is I'm going to do x2 from our starting point or our origin will be point C going this way. So let me draw that out for you guys. So it is going to still be within the region BC, but instead my origin is going to be at point C. So my body diagram would be my beam here with my moments right here of 200 pound-feet going counterclockwise. So my cut has to be somewhere within the region BC. And we know that from here to the cut is going to be x2. And from there, we simply just have to include my shear and moment. So since this time the cut is to the left side, we know that our shear force will be going upwards and my moment will be going clockwise. So as you guys could see, by doing it this way, we have less things to work with, making it more simpler. So I'm going to be taking the sum of the forces in the y direction to solve for my shear force. And as we could see, our shear force is our only vertical force. So we know that our shear force equals 0. And we know that this is going to be true. Meanwhile, x2 is greater than 20 feet and less than 30 feet. Well, less than or equal to 20 feet. To 30 feet, sorry. And then for our moments, I'm going to be taking the sum of the moments about the cut. So we have our moment going clockwise. So that's a negative moment. And then from there, we have our 200 pound-feet moment as well going clockwise. So another negative moment. And then we know our shear will not be creating a moment since it is right there at the point where we're taking the sum of the moments. So this has to equal 0. So we know that our moment is going to be equal to negative 200 pound-feet. And then from there, once again, we know that this is true. Meanwhile, our x2 is within the ranges of, while our x2 is equal to, no, I'm so sorry, you guys. Since I took my origin to be a different place, technically this isn't how we would write it. I'm so sorry. Since my origin place is at point C for this part, then 0 would be here and it would be inwards. So technically then valid um my valid limits would then technically be considered with the origin at A. So let me specify that. So with origin at C, this is valid. Meanwhile, x2 is greater than or equal to 0 and less than or equal to 10 feet. Because now we're looking at it from here. So this is valid. Meanwhile, it's greater than or equal to 0 and less than or equal to 10 feet. So there we go. I forgot to modify the limits now that I took my origin at a different place for this part. And then the same thing would be here. So with the origin being at point C, once again, this is valid. Meanwhile, it is greater than or equal to 0 feet. And once again, less than or equal to 10 feet. And with that, we are done with this problem. So once again, this problem was asking us to, for the beam given below, to derive the moment functions for regions A, B, and BC, and to use the position variables x1 and x2. But as you guys knew, we took x2 instead of it being this way, since it would just require more work. I took x2 starting from here going this way. But the first step we did is first we found our concentrated force of this constant loading that we had. From there we solved for the values of our reaction. And then from there, we drew a free body diagram of our region AB and our region BC. And then from there, simply included our shear and moment based on sign convention. And then from there, we simply just solved for those functions. Thank you guys so much for watching this video. Please feel free to give this video a thumbs up if you found this video useful. And also feel free to subscribe to our channel if you guys would like to see more videos like this one.